So there are times out there in the real world where you actually will be talking with someone about a molecule. That probably doesn't happen very often, but it does happen. So I'm sure you're all familiar with water. You might, in a formal scientific setting, you might be describing water to someone and you might call it H2O. Or you might be talking about table salt and you might sort of describe the atoms that make up table salt. So I just want to set in your mind that there are times when you might want to communicate or describe a molecule to other people, and there are times when other people may need to describe a molecule to you. Now, you could do it this way. You could describe it in a very detailed way. You could draw a picture for a person and you could say, look, I am working with water, and this is really what I'm working with. It's an oxygen atom, and that oxygen atom is covalently attached to two hydrogens, one over here and one over here. And under some circumstances, it might be worth spending all of this time describing how the atoms in a water molecule are actually attached to each other. But there are other times when this is basically describing a molecule in this level of detail is just a waste of time. And people basically need a simpler way of describing a molecule. So I'm sure you're all familiar with the fact that you can describe water in this way. A lot of times people will call it H2O. And this is just a quick summary of this picture over here in the center of the slide. In other words, you don't sort of draw each atom out and you don't try to describe how big each atom is relative to the other atoms. You just say, look, I have two hydrogens and an oxygen, and they're all attached to each other in some way. And this is the more common way that people use to describe molecules to each other. In other words, for the most part, you're probably not going to draw this. You probably will either speak this, you'll say H2O, or you'll write this out if you need to write it out and explain it to someone. And again, many of you are probably familiar with the fact that writing out what a molecule is in this way is called a chemical formula. This is basically just a simple way of describing the atoms in a molecule. And we're going to talk about that in more detail on the next few slides. So again, here this slide is going to be practicing how to write the chemical formulas of different molecules. So if you remember, our definition of a molecule is two or more atoms that are attached to each other. And to write a chemical formula for a molecule, what you do is you write the symbol for each atom that's in your molecule, and then you write the number, how many of each atom, as a subscript to the right of that atom. And you've already seen that with water, but I'll show it to you again. So you write that water has hydrogen atoms and it has an oxygen atom. So you write the symbol of each atom. You write H for hydrogen, O for oxygen, and then you write how many of each atom as a subscript. This 2 here is basically referring back to the hydrogen, and it's saying, look, water has 2 hydrogens, and you don't write the 1, but it's implied to be there, and a water molecule also has 1 oxygen. So that's what that's what the subscript means. You could, if you wanted to, if you were a little bit wordy, you could say, look, my water molecule is made of 2 hydrogens, so that's what this 2 is referring back to the H, and it's made of 1 oxygen. In practice, no one ever writes the subscript of 1 here referring back to the oxygen, just because you'd be writing the number 1 a lot of the time. So if you don't write the number 1 is implied, although this kind of technically would be okay. People tend not to write it that way. Here's a different molecule. This molecule over here has 1 carbon because there's no number written to the right of the letter C, and C is the abbreviation for carbon. So it's implied that there's 1 carbon attached to 2 oxygen atoms. And this, you don't need to know this, but this is the formula for carbon dioxide. So carbon dioxide has 1 carbon attached to 2 oxygens. Again, if you were feeling a little wordy, you could write C with a subscript of 1, which means I have 1 carbon, and then you could write O with a subscript of 2. And this is basically just a more detailed way of writing this, of writing CO2 off to the left here. Virtually everyone on the planet who writes chemical formulas writes it this way. You probably will never see it this way, but I'm writing it that way just to illustrate the point that the number 1 is implied. Now at this point I'm going to give you a handful of practice problems just to try to make sure that you sort of get the concept of what a chemical formula is telling you under your belt. So here's the first example, and what I'll do is I'll sort of go through each molecule. This is the chemical formula for one type of molecule, and I'll pause at different points, and you can pause the video and basically try to figure out the answer before I give it to you. So this is actually the chemical formula for glucose, which is sugar that we use in our bodies, but I'm more interested in understanding the chemical formula. So the first question that I would ask you is, how many carbon atoms does this molecule have? And again, you can pause at this point, and hopefully you will see that the 6 here is telling you how many carbon atoms you have. The 6 refers back to the carbon. So this particular molecule has 6 carbon atoms. Next question would be, how many hydrogen atoms does this molecule have? And again, I can pause. You can try to figure this out. And hopefully you will see that this molecule has 12 hydrogen atoms. And I can ask the same question about oxygen. How many oxygen atoms does this glucose molecule have? And again, you can pause, and hopefully you will see that the 6 here refers back to how many oxygens there are. So a glucose molecule has 6 carbons, 12 hydrogens, and 6 oxygen atoms. And that's basically how you read a chemical formula. And if this seems very easy to you, they may get a little bit more complicated as we progress. So here, this one may not be too difficult. This is a nitrogen molecule. So again, remember that molecule means 2 or more atoms attached to each other. And I could ask you, how many nitrogen atoms are in a nitrogen molecule? And you can pause, look at this, and you can see that there are 2 nitrogen atoms for every 1 nitrogen molecule. And that's basically what the 2 means. Here's perhaps a more difficult one. So again, this is a formula for a molecule called acetic acid. If you're interested, acetic acid is the main ingredient in vinegar. It's what makes vinegar taste tart. And so the first question is, and I will pause again, how many carbon atoms in this molecule? And I'll pause. You can look, and you should actually see that there are 2 carbon atoms. There's one over here, and the 1 is implied to be here, but there's one also near the middle of the molecule. So this may seem a little bit tricky, right? You would think that you should always bundle each of the atoms, but it turns out that in real life they will not always be bundled, and I will explain a little bit of why that is in a minute, but I'd like to go through the rest of the molecule. So the next question is, how many hydrogen atoms does this molecule have? Now pause for a second, and you will hopefully see that this molecule has 4 hydrogens. 3 over here near the left-hand side, and there's 1 extra hydrogen over here on the right-hand side. The 1 is implied again. So this molecule has 4 hydrogen atoms. Then the final question is, how many oxygen atoms does this molecule have? I will pause for a second again, and you can see that it has 2 oxygen atoms. So the acetic acid molecule actually has 2 carbons, 4 hydrogens, and 2 oxygens, even though the atoms are a little bit split up in this formula. Now, you can ask yourself, well, was the teacher actually just trying to trick me in splitting up the atoms in this formula? The reality is that no, I wasn't trying to trick you. You could, if you wanted to, you could write the formula for acetic acid like this, which is probably what you would have expected. And however, there are many times when chemists actually write the chemical formula for things like acetic acid out in this weird way where they split up the atoms. I won't go into too much detail about why they do this. We'll talk about it much later in the course. But the reality is that splitting up the atoms in this way and writing a more extended chemical formula is actually sending a message to the reader who is accustomed to seeing this. The message is basically trying to explain how each of these atoms is attached to each other. This formula down here, even though it's correct and it's the formula for acetic acid, gives the informed reader less information about how the atoms are actually attached to each other. This formula up here is supposed to give the chemist who's been around the block for a while, this formula is supposed to give them a little bit more information about how those atoms are attached to each other. So I don't expect you to know what it's actually trying to tell you, and we'll talk about that later in the course, but just keep in mind that you will very often see chemical formulas written out like this because there's added information there. But you should be aware that this formula is still telling you that this molecule has 2 carbon atoms, one over here and one over here, even though they're not bundled next to each other, or bundled with each other, I should say. And this molecule still has 4 hydrogen atoms, 3 over here, 1 over here, and then 2 oxygen atoms. So again, you need to scan across the entire molecule just to make sure that you haven't missed anything. And then just to drive home the punchline, if the subscript in a chemical formula isn't there, it means that there's only one of that atom. So over here, there's no subscript, so it means 1 carbon. There's no subscript here, it means another carbon. No subscript on the O, no subscript on the second O, and then no subscript on the H. Again, implying one of each of those. So that's sort of an introduction to how to read a chemical formula. I'm going to show you a little bit more complicated example on the next slide. So this is the formula that gives people trouble. Here's the chemical formula. I can give you the name of the molecule. It's called calcium nitrate. And I'm going to ask a few questions, and you can pause and try to answer the questions. The first question is, how many calcium atoms does this molecule have? You can pause the video, and the answer is that because there's no subscript immediately to the right of the symbol for calcium, there's only 1 calcium in this molecule. The next question, which you may or may not know the answer to, is how many nitrogen atoms are in this molecule? Again, you can pause and think about this. The answer to how many nitrogen atoms in this molecule is that there are 2 nitrogen atoms. Even though there's no subscript immediately to the right of the nitrogen, it means that there's 1 nitrogen here. But this subscript of 2, outside of the parentheses here, this subscript of 2 basically means there's two sets of everything that's inside of the parentheses. So if there's 1 nitrogen inside of the parentheses, this 2 means that there are actually 2 sets of those 1 nitrogens. So there are 2 nitrogens inside the parentheses. The next question, again, for the last atom is how many oxygen atoms in this molecule? You can pause. And the answer to how many oxygen atoms in this molecule is that there are 6. Again, there are 3 implied to be inside of the parentheses because of this subscript of 3. And the 2 is basically saying there are 2 sets of O3s. So if there are 2 sets of O3s, there are 6 oxygens. So this molecule has 6 oxygens. Another way of basically figuring this out is you multiply the subscripts together. So 2 times 3 is 6, 6 oxygens. There's a 1 implied to the right of the nitrogen. 2 times 1 is 2, so there are 2 nitrogens as well. So again, we've answered these questions. How many calcium atoms, how many nitrogen atoms, how many oxygen atoms? So, and you know, if you think about it, you could basically say, look, couldn't I just write the formula as CaN2O6? And the reality is that yes, you could write it this way, and this is a perfectly valid way of writing it. However, writing it in the way that I've shown at the top is actually giving a little bit extra information. What it's telling you, or what it will hopefully tell you as you get this under your belt, is that the NO3s travel as a pack. They travel as a group, and you can have 1 set of them, you can have 2 sets of them, and it just so happens that this molecule has 2 sets of NO3s, and that's sort of how the nitrogens and oxygens travel with each other in this case. If you look at this formula down at the bottom, it doesn't really tell you that type of information. So chemists tend to favor writing the formulas this way for that reason. There's less information being told to the chemist down here than there is up here, even though you're talking about the same molecule. One thing to point out, I want to point out a few things that you shouldn't do. You don't write the formula like this. You don't write calcium and then a 2 in front of the parentheses. That's just not done. It's not the convention that has been decided on by chemists. If you're talking about two sets of NO3s, you take this 2 and you put it as a subscript outside of the parentheses. And that's a common mistake that students make, but I really don't want you to make this. This is basically, chemists never write it this way. The other thing, and we're going to get into this in more detail on the next slide, is you can put a 2 in front of the entire molecule. So here the 2 was in the middle of the molecule, it basically split it in two. Here the number 2 is written to the left of the entire molecule, 2CaNO3 2. In this case, you could write it that way, but the 2 means something. It means 2 of the entire molecule over here. It means 2 of everything to the right. So what it's saying is, if this molecule is called calcium nitrate, and it is, a 2 in front of it means 2 calcium nitrates. The 2 as a subscript over here means 2 sets of whatever is in the parentheses. And again, this may seem obvious to some of you, and it may seem confusing to other people. If it's confusing, this is something where you're just sort of going to have to essentially force yourself to memorize what the conventions are. Subscript outside of the parentheses means 2 of everything inside of the parentheses, and the number to the left of the molecule means 2 of those molecules. And that's just something you're going to have to sort of become accustomed to. So I'm not going to spend too much time on this slide. There are a handful of formulas, some of which we've gone over already, but this will just serve, I'm just going to sort of quickly go through a number of these formulas and then pause at the last formula because that's the hardest one. Here, I could ask you, look, this is a water molecule. How many hydrogen atoms does it have? Well, you look at the subscript, you say 2 hydrogens. How many oxygen atoms does it have? It has 1 oxygen. Here, this is a different molecule. How many carbons? 17. How many hydrogens? 14. How many oxygens? 4. How many sulfurs? 1. What does this mean if I put a 2 in front of the H2O? As I said on the last slide, this basically means 2 water molecules. Now, in reality, I'm cutting a corner here. I'm telling a little bit of a lie. The reality is that it can mean 2 water molecules. It could also mean 200 water molecules, or it could also mean 2 billion water molecules. And I'll get into the details of why I'm saying that in case I have a suspicion that that may be a little bit confusing. If it helps, at least initially, think of the 2 here as meaning 2 water molecules. But you'll see in the next couple of sections that that's not always the case. So if it helps you to think of the 2 in front of the H2O as just meaning 2 water molecules, here's number 1, here's number 2, that's good for the moment, and that's good enough for the moment. But you will see situations like this, where you'll see a number in front of a molecule, but it won't be a whole number. It'll be something like, what does 3.58 H2Os mean? You can't have 3.58 water molecules, but you can have 3.58 million water molecules. So what you'll see in the end is that the number in front of a molecule can have a flexible meaning depending on the situation, and we'll explore that in more detail in the next few sections. So just keep that in mind, that you can have these weird numbers in front of a molecule. And then here's the last one, just to focus on these parentheses again. We can ask how many magnesiums in this molecule. Well, here's the symbol for magnesium. There's no subscript immediately to the right, so there's 1 magnesium. Then we could say how many chlorines in this molecule. Well, inside of the parentheses, there's no subscript immediately to the right of the chlorine, so there's 1 chlorine inside of the parentheses. But the 2 outside means that there's 2 sets of everything inside, so there are actually 2 chlorines in this molecule. And then finally, I could ask you how many oxygens in this molecule. Again, 4 oxygens inside the parentheses, The 2 means 2 sets of those 4 oxygens, which means 8 oxygens total in this molecule. So hopefully you understand the concept of what these subscripts mean. Hopefully you understand the concept of what these parentheses mean and what the subscripts outside of the parentheses mean as well. However, if this is difficult for you, you can email me and we can hopefully talk about it and discuss it in more detail. But to summarize, you basically just learned how to read chemical formulas. And in the end, after a fair amount of practice, reading chemical formulas should become second nature to you. You should be able to look at a formula and say, oh, it has 32 hydrogens, and it has 7 carbons, and things like that. And then, again, just because it will become second nature to you, if I give you the formula for some compound or molecule, you should be able to tell me what the different atoms are and how many there are of each kind. So that's the end of the introduction to chemical formulas. The next section will require you to understand how to read a chemical formula.